Hello and welcome to the 28th lecture in this series. Today I'll begin by talking a bit about smooth maps with reference to submanifolds, and then we'll move on to vector fields on manifolds. So let's start with smooth maps. So here's the proposition. So I have the first one is that let f from M to N be smooth. As usual, M and N are manifolds, smooth manifolds, and I have a smooth map. If S contained in M is a submanifold, then the restriction of F to S from S to N is smooth. So if I have a smooth map on the big manifold, and if I have a submanifold of the domain, and if I restrict the smooth map to the submanifold, it will continue to be smooth. Second thing is let F from M to N be smooth. This time, if S I take a submanifold in the image is a submanifold, and suppose I know that the image of F is actually contained in S. Then I can regard F as a map from M to S. The claim is that this map is smooth. And the proof of, I won't go into the details, the proof immediately, this follows from 1 and 2 both follow from checking the definition, checking smoothness, using slice charts. The way we define smooth maps, we have to choose some charts and then see what the map looks like. So in both these cases, use slice charts for the submanifold and pretty much any chart for the other things, and then you are done. Now the use of this proposition is that in at least in one case, in one case it's easy. It will be easy to check that the big map F on the whole manifold M and N will be smooth. Then one doesn't have to bother using charts for S and so on. One can directly say that the restriction is smooth in the first case, and in the second case as a map into S is smooth. So as a corollary, so the corollary is the following. If F from, this is the case I had in mind, we know if F is a map from Rn to Rm, we know that smoothness is equivalent to the usual definition of smoothness that we had. And so one can basically check that f is smooth relatively easier in an easy way. And if S contained in Rn, T contained in Rn are submanifolds, with f of S going to T. So let me just change this, write S in a slightly better way, S. So suppose I have this condition that if this submanifold is taken to this submanifold, then I can regard F as a map from S to T, and this map is smooth. So in short, if I have a map on the, one can proceed to use this corollary, one can proceed in the sort of reverse direction. So suppose I have a map between two submanifolds of Rn and Rm, F from S to T. If I know that F extends to a smooth map between the corresponding Euclidean spaces, then I know that the original map I had is smooth. So the point is that I no longer have to worry about charts and so on. Just if it extends to whole of Euclidean space, just work with the usual definition of smoothness in terms of partial derivatives, and one is done. So as an example, let's take something that I had briefly touched upon in the beginning of this course. So let's take a map from, let's take F. I'll start with a map from Sn to Sn, the n-dimensional sphere, and this f of x equal to Ax. So f from S, let's start A in the orthogonal group On, and so I define f of x equals Ax for all x in Sn. So it's just the rotation matrix acting on elements of the sphere. A rotation matrix acting on elements of the sphere, and we know that if norm x, since A is an orthogonal matrix, if x norm x equal to 1, in other words, if x belongs to the sphere, then if norm x equal to 1, then norm of Ax is also equal to 1. So this map is a well-defined map from Sn to Sn. And now suppose I want to claim that this map is smooth. The straightforward approach would be to start with some charts on Sn and then express the map as a map between two open sets in Rn, and then check the smoothness. But that's a bit inconvenient. So since we have to use charts, and the formula for the chart is, well, in this case it's not that complicated, but still one can avoid all that just by using the proposition, the corollary here. By the corollary, no, before the applying the corollary, let's note that f is the restriction of the map x going to Ax from Rn plus 1 to Rn plus 1. So since well, this map from Euclidean spaces is just a linear map and we know it's smooth. Therefore, immediately the corollary tells us, the corollary implies that f from Sn to Sn is smooth. So we can avoid the use of charts altogether. Right. So that concludes our brief discussion of smooth maps and the regular value theorem. Now let's move on to the next topic, which is the notion of a vector fields. Vector fields on manifolds. So a vector field X on M is an assignment of a tangent vector xp in TPM to every p in M. So to every point in the manifold, we are picking out a specific tangent vector x, which I denote by x subscript p. And this assignment is required to be smooth in the following sense. First, I'll give an abstract definition of a smooth vector field. Then we'll see what this means in local coordinates, in a coordinate chart. Well, following sense. So if f is a C infinity function, then the function g subscript f from M to R defined by gf at a point x is, I have a vector field. So at each point x, I get a tangent vector at the point x, which is a derivation. So I can act this derivation on the function and I get a real number. So the point is that if I start with a vector field and if I'm given any function, I'll get a new function from M to R. And we require that this function gf is smooth. So this is what we mean by smooth vector field. Now, so this has a, well, every notion that we define can be, we can always use a coordinate chart to see what exactly it means. So here, for example, let's see what this notion of smoothness means if I take a coordinate chart. So I'll give an equivalent definition of smoothness. Smoothness in a coordinate chart. To do this, let's observe a couple of things. Note that if x is a vector field on M, and f is a C infinity function on M, then we get a vector field fx, f times x, and this is defined. So in order to say what a vector field is, I have to specify what tangent vector we get at every point. So let's take a point P, and this is defined to be f of P, which is just a real number, times xp, which is the tangent vector given by the vector field x at the point P. Then we get a vector field, and it's clear that this new fx is also smooth. Fx is smooth in the sense that we had defined earlier, i.e. if I take another C infinity function, if phi belongs to C infinity M, then this what I called this gf, then the function gf just consists of taking the vector field at the point x and acting it on the function f. So here let's take a point x. This is sent to now the vector field is fx at the point x acting on phi, which is fx, which by definition is fx times x, this. And this, with our earlier notation, this is fx times g phi of x. So in other words, this new, if I start with any phi, the new function whose smoothness I am concerned about is just the product of this fixed function f and this function g phi, which I know is smooth because x itself is smooth. So f times g phi will be smooth. This is smooth. So in short, I can just given a smooth function, given a vector field and a smooth function, I can multiply the vector field by the smooth function and get another vector field. So intuitively one thinks of it like this. So after all, what is a vector field? Schematically, at every point I have a tangent vector, and if this is my vector field x, and if I have a function, all I am doing is I am just taking these tangent vectors and multiplying by the constant at the point x. I will multiply by the constant f of x. So this vector, it will shrink or expand, and it might get reversed also depending on whether f of x is negative or positive. So, but essentially we stay along the same line at each point, and but the direction or the magnitude of the vector can change depending on f. Right. So that is the one observation which is useful. Second thing is that, so this is one thing. Let U belong to U subset of M be an open set. Since we have already seen that the tangent space at U, tangent space at a point P in U is actually we have identified with tangent space to M itself. For all P in U, if X is a vector field on M, then X restricted to U is a vector field on the manifold U. We know that every open set in a manifold is itself a manifold. So I can just restrict it to look at the values of X for points in U, and I get another vector field. I get a vector field on U. And as for smoothness, I know that the original vector field on the all of M is smooth, and if I want to say that this is smooth, it just depends on this identification that we have here. So for smoothness of X restricted to U, recall that after all, how did we identify the tangent space to U with the tangent space to M? Well, suppose recall that X restricted to U, if I have a C infinity function, recall that if F is a C infinity function on U, then the action of X restricted to the action of X Q X restricted to U at the point Q, maybe I should put the Q outside, acting on this function F. The point is that a tangent vector to U will act on C infinity functions which are defined on U, not necessarily on all of M. But we saw that we can always extend any such function on U close to a point, extend to a C infinity function on M such that the extension agrees with the original one in a neighborhood of any given point Q. That was our process. So this was defined to be XQ of phi F, where phi is a C infinity function supported in U and identically equal to 1 in a neighborhood of, we have been using this repeatedly, neighborhood of the point Q. This will immediately imply that, well, what I have written here is just the definition, the identification that we have here. So I just spelled out this identification explicitly in this. And if one wants to actually check smoothness, one goes by this identification. So I won't go into that. It follows immediately from this that if F is a, so in fact, if F is a C infinite, this identification also shows immediately that if F is a C infinity function on U, then this new map Q going to this thing here, what I have here is actually a smooth function on U, because this is a, the right hand side is in fact will be a smooth function on all of M. So when I restrict it to U, I get a smooth function on U. So it's quite clear that I get something smooth. Right. Now, given this, let's fix a chord. Now, next thing is let u phi be a coordinate chart. We have a basis, we have seen this before, we have a basis for TQM for all Q and U. So, namely, we know that by definition this is phi is a diffeomorphism onto U1 in Rn, and on Rn I have a natural basis for the tangent space at every point, namely the partial derivatives along the n directions evaluated at that point. So, and since phi is a diffeomorphism, the derivative of phi is a linear isomorphism. So, I can just use the derivative to transfer this basis to this. Actually, I'll have to go in the opposite direction. Phi inverse will be from here to here. So, at each point I have a basis. I use the derivative of phi to push this basis to basis of the corresponding point in the tangent space. So, what I do is d phi inverse. So, if I start with a point Q, suppose I want a basis for the tangent space at Q. I go to phi of Q here, this is phi of Q, use the basis here and use the derivative. So, d phi inverse at the point phi of Q of the basis in Euclidean space, which is del by del xi evaluated at phi of Q. So, this derivation I just push it back to this. So, look at this, I equals 1 to n. And this is a somewhat cumbersome notation the way I have written it. Normally, this is denoted by just del by del xi at Q. There is a chance of confusion with this notation, but it's one has to keep in mind that when you see this del by del xi evaluated at Q, what one literally means is what I have here, this thing. So, as long as that is kept in mind, we can freely use del by del xi at Q. So, we have this basis, and now we also had a vector field. I started with a vector field on the all of M. The second observation was that I can restrict it to U and get a vector field on U. Well, so let's express. We can write x at Q. So, this is supposed to be, so this is the restricted vector field. I'll drop the notation x restricted to U. Instead of this, I'll just use x itself. So, with that change, so x at Q will be, it's a tangent vector. By definition, it's a tangent vector at Q. So, it's an element of TQ U or TQM. So, and I already have a basis, so I can write it as sigma AI Q, and using this convention, so I write it as del by del xi at Q. Here where AI are now functions from U to R. So the claim is that, which I'll prove next time. So what I want to claim is the smoothness of the vector field proposition X is smooth if and only if the AI are smooth. Alright, so we'll stop here. I'll resume with the quick proof of this proposition next time. Thank you.